Logic circuits. This presentation follows on from the logic gates animation. In it, we will look how you go about creating logic circuits and the associated truth tables. Logic gates can be combined to produce one or more outputs from two or more inputs. We call such a combination a logic circuit, even though we are only referring to the flow of signals from the inputs to one or more outputs. We are not referring to the technical details of a full electronic circuit. In the logic circuit diagram here, input A goes into the AND gate, while input B goes into both the AND gate and the NOT gate. For any logic circuit like this with two binary valued inputs, there are two squared possible combinations of values. In other words, 4 possible input combinations. In the examination, you will need to be able to produce truth tables for circuits like this to show the values of an output. To do this, we draw a table containing each of the 4 combinations of input values to show the values of an output, which we call X in this case. We place these 4 combinations in a consistent order in the rows in the truth table, with input A as the 2's column and input B as the units column. Since it may be quite hard to think through the behaviour of all the relevant gates to work out the output of a logic circuit, it is usually helpful to include the columns in the truth table for the values at each intermediate output, between the inputs and one or more outputs. In this example, these intermediate outputs are labelled as D and E in the circuit diagram. To show this in the truth table, we include a new column for the values of the intermediate output D, which will show the output from the AND gate from inputs A and B. We also include a column for the values of intermediate output E, which will show the output from the NOT gate from input B. D and E form the inputs to the OR gate, for which we need to work out the values for output X. So we adapt the output X column heading to reflect this. Now, using our knowledge of the behaviour of the AND and NOT gates, we first complete the columns for D and E. Then we use our knowledge of the behaviour of OR gates to complete the column for X. Notice that we can write the words AND, OR, NOT, NAND, and NOR as operators in logical equations that express the behaviour of the outputs D, E, and X. We can also substitute the expressions for D and E in the logic equation for X using brackets to indicate that the logical operation within the brackets takes priority. This is our logic statement. So remembering that 1 is a numerical value representing true, we can read the statement as meaning the following. This agrees with the truth table that was produced. 3 inputs and 6 gates will be the most complex logic circuit for which you will need to be able to produce a truth table. Here is an example with 3 inputs. For any logic circuit with 3 binary valued inputs, there are 2 to the power 3 or 8 possible combinations of values, so we will need 8 rows in the truth table. To work out all 8 combinations and place them in a consistent order in the rows of the truth table, we can count from 0, 0, 0, 0 in binary, to 7, 1, 1, 1 in binary numbers, with input A as the 4's column, input B as the 2's column, and input C as the units column. So let's look at the truth table for this logic circuit. As with our first example, we add the columns for each of the inputs, A, B, and C, and enter the truth values in the correct logical order. Again, we also include columns for the intermediate outputs E and F to make it easier to see what the final output X should be. We enter the values for these based upon the values in the input columns and our knowledge of the logic gates AND and NOR. Finally, we enter the values for output X, which are determined by the values for the intermediate outputs E and F and our knowledge of the OR logic gate. So you have seen how to produce a truth table and a logic statement from a logic circuit diagram. But what if you were asked to draw a logic circuit diagram to represent a logic statement or condition that you are given? In this example, we have a condition. We can simplify this to produce this logic statement. To draw the diagram, start with the brackets first. In this example, we start with A and B. We use the AND logic gate and join inputs A and B to it. Then we move on to the second bracket, A and NOT C. We add input C and place the NOT gate after it, joining C to it. Then we add in another AND gate and join input A and NOT C to it, using the appropriate indicator to link input A and the AND gate. We then complete the circuit diagram by adding the OR gate and joining the two AND gates to it, and including the output X. In the exam, you may then be asked to complete a truth table for the completed circuit, so let's look at that next. The logic statement will help remind us what we need to enter into the truth table. To complete the table, we first add in all the possible combinations of the inputs A, B, and C. Remember to start with 0, 0, 0 and finish with 1, 1, 1. As the truth value for X can happen when both A and B are true, first look for all the combinations of where A and B are true, or 1 in the table, and for those combinations, place a 1 in the corresponding row in the X column. In this case, there are two possibilities of where A and B are 1 in the last two rows. Then look for the combinations of A and not C and place a 1 in the X column against those combinations. In this case, there is only one combination, the 1, 0, 0 row. For all the other outcomes, place a 0 in the X column. This completes the truth table for our drawn logic circuit. Let's finish by looking at solving a problem using logic gates. This problem is taken from an exam paper from a few years ago and therefore is in the style that you may get in an exam. The output X equals 1 is generated under the following conditions. First, we write the conditions for when X equals 1 into a logic statement, which is shown here. Next, starting first with the brackets, we begin to draw the circuit. In this case, G and not C is drawn like this, with the input G linking to the AND gate, and the input C passing through a NOT gate and then on to the AND gate. We then draw C and not L, with both inputs linking to another AND gate, and input L first passing through a NOT gate. Finally add the OR gate, linking it to the AND gate and adding output X at the end. The logic circuit is now complete. So let's now complete the truth table for this circuit, as this is something you will most certainly be asked to do in an exam. The logic statement above the truth table will help to remind us of what we need to enter into the table. First, we enter the values for each input into the table in the logical order. As before, we then start with the first bracket in the statement, G and not C. We look for the combinations where this is true, placing a 1 in the X column against those combinations. In this case, rows 1, 0, 0 and 1, 0, 1. Then we look at the second bracket in the statement, C and not L, and do the same. In this case, we place a 1 in the rows 0, 1, 0 and 1, 1, 0. All the other rows will be 0, as they do not comply with the condition in either bracket. We've now completed the truth table as well as the logic circuit diagram. When practicing logic circuits, it can be helpful if you use a program such as Logism to draw the circuits, and then test that you have correctly completed the truth table. However, remember that in your exam you will have to be able to draw the logic gates freehand, so make sure you know the symbol for each gate and that you can draw them correctly. Good luck!